Here we go. Very good. It is my great pleasure and honor to introduce Joe Kapusta today. Joe has a long and very distinguished career in nuclear physics. I remember a story he once told me that he met Hans Bethe, and he told Bethe what he was working on, and he said, "Oh, it's just a little problem." And Bethe interjected and said, "No, it's good working on little problems. That's how you get to solve big problems." And I think the story of Joe's career is a set of problems that seemed little at the time, that through his technical excellence and his good physical sense have become very great problems. One that's dear to my heart is when shortly after he was a graduate student at Berkeley and graduating in 1978, that he computed the free energy in QCD at non-zero temperature and chemical potential at a resummed set of diagrams to two-loop order, the first term of order g cubed in the coupling constant. And that's engendered a great field of computing the free energy at non-zero temperature and density, which is now being pushed to four-loop order. He's known as well for contributions on dileptons and other electromagnetic probes, on the analysis of shear viscosity. He's famous for a great textbook on the field, and he's also served as an associate editor of Physical Review C for over about 25 years, and he was recently appointed lead editor for Physical Review C, something which I think many of us welcome very much. And so with that, I'd like to introduce Joe. Would you like to go ahead, Joe?
Thank you very much for the kind introduction. Screen share. So over a bit. So this morning, today, I would like to tell you about some work that I've done with a graduate student, Tom Welly. He's finishing his PhD this fall, defending his thesis probably in December. And Chris Wesselberg, sorry, that's our managing editor, Christopher Plumberg, who was a postdoc with us, Uli's student, postdoc with us. He was a postdoc in Lund, University of Illinois, and starting this fall, he is a junior faculty member at Pepperdine University in Malibu, California. So the point of this, as we all know, in the beam energy scan collaboration, is to try to understand whether or not there is a critical point in the QCD phase diagram, and if there is, how do you describe it theoretically? Well, there are many model calculations that predict the existence of a critical point. But when you do model calculations, almost invariably, you end up with mean field critical exponents. In addition to that, there are descriptions of critical equations of state, but they don't include a background. They just focus on a very close neighborhood of the critical point. How you merge that into a background describing all the rest of the phase diagram is not a solved problem, and there is no unique solution to that. So our goal in these works, which I will describe too, is to construct an equation of state which is in the same universality class as the liquid gas phase transition and the 3D Ising model. Now, in this construction, we would like to have free parameters, and these free parameters then should be adjusted by putting the equation of state into hydrodynamic calculations, for example, and varying these parameters and comparing to experimental data. And in this way, it would be great if we could infer, for example, what is the critical temperature, critical chemical potential, critical density, and so on. Such an equation of state is also needed for modeling neutron star mergers. As when neutron stars merge, they reach very high temperatures, at least 50 MeV, perhaps 100 MeV, even a little bit more, very high baryon densities. So it's not just in our very specific field of heavy ion physics, but more broadly in high temperature, high density hadronic matter. So I will describe two very different mathematical constructions for how to do this. So the first one was done in collaboration with both Tom and Chris. And we worked on this problem for a very long time. And off and on, off and on. Chris was a postdoc here, and then he was in Lund and finally Illinois before we finally came to a resolution, the solution, how to do this. So we were motivated by S-shaped curves that you see in first order phase transitions. If you plot pressure versus density, isotherms, you always see S-shaped curve. You do a Maxwell construction or stable regions, metastable regions, unstable regions. So after a lot of trial and error, and we came up with the following mathematical model. So the important thing, the most important ingredient here are these functions which we define to be Q plus and minus. And these functions involve other functions. One of them is lowercase r, and that tells you how far you are away from the coexistence curve. The notation is mu sub x of t is the chemical potential describing the location of the coexistence curve. And of course, it terminates at a critical point. So this function lowercase r tells you how far away you are from that. You want to know that because if you get far enough away from the critical curve, you should recover your nice smooth background equation of state. Similarly, in the temperature direction, there's a quantity we define to be delta, and delta tells us how far we are away from the critical point, critical temperature. There are parameters in here. The two most important ones are two exponents, k and p. And these two exponents need not be integers, or they need not even be rational numbers. And they will be related to critical exponents that we know and love in phase transitions. So how do we construct the pressure? We construct the pressure by taking the background pressure as a function of temperature and chemical potential and multiplying it by a function capital R, which is constructed from these Qs. So if you are above the critical temperature at any value of the chemical potential, we construct the function R, capital R, in the way that I've shown here. So it involves the delta, which is above. It involves the Q plus and the Q minus. And it also involves a coefficient function A, depending upon temperature. Okay. If you're below the critical temperature and you are at chemical potentials below the coexistence chemical potential, then we're basically in the hadronic phase. Most of the matter is really composed of hadrons. And in that case, this function capital R, hadronic phase, is given by the formula shown here. It involves the function Q minus. And if you look at Q minus at the top of the page, that has the lower sign in front of the function lowercase r of t and mu. If you're below the critical temperature and above the coexistence chemical potential, then you're basically in the quark-gluon phase. And then that involves the function Q plus. So it's not obvious at all how this construction comes about. Like I said, it's trial and error over actually several years of effort. So what can you do with this? Well, let's check everything. So let's suppose you approach the critical density along the critical isotherm. In that case, the pressure minus the critical pressure should be proportional to the sign of the density between the actual density and the critical density. And its absolute value, the difference, to the power delta. So delta is one critical exponent. And from the construction I just showed you, delta turns out to be 1 over K-1. Now, it's usual to define another temperature, a reduced temperature, lowercase t, which I will use sometimes interchangeably, T minus Tc divided by Tc. Now, if you approach the critical point from above, then the susceptibility and heat capacity diverge. The susceptibility goes like T to the minus gamma, and we calculate from our construction that gamma is 2 minus K times P. The heat capacity diverges with an exponent alpha, and from our construction, alpha turns out to be 2 minus K times P. If you approach the critical point from below, how do you approach it from below? You approach it from below along the coexistence curve, from the right or from the left. In that case, the susceptibility also goes like reduced temperature T, minus sign in front because T is negative, to the power minus gamma. It's the same gamma in terms of K and P as the one above. The heat capacity goes like minus T to the power minus alpha, with the same expression for alpha in terms of K and P as above the critical temperature. And then finally, the fourth critical exponent is the density difference along the coexistence curve. So it's the density of the liquid phase minus the density of the gas phase, or in our case, the density of the quark-gluon phase minus the density of the hadronic phase. And that is proportional to minus T to the power beta. And from our construction, we calculate beta to be K-1 times P. So at first we were concerned, well, we have only two exponents, but there are 4 critical exponents. Well, it turns out, I don't know if this is magic or we got lucky, but the critical exponents satisfy the known relations, namely alpha plus 2 beta plus gamma equals 2, and gamma equals beta times delta minus 1. So our K and P can be written in terms of any 2 of these, and then the other 2 are automatically determined. That's nice. There's something special in this construction. Critical exponents in a particular universality class are universal, but so are ratios of critical amplitudes. So the C plus, the C minus, the chi plus, the chi minus, those ratios are universal, not individual values, but the ratios. It turns out in our construction that the ratio of these critical amplitudes are very simply related. So C plus over C minus to the power 2 minus K turns out to be 4 times chi minus over chi plus to the power K. This is a relationship that is satisfied numerically. And I asked a lot of my colleagues in condensed matter physics, well, do you know of any such relationship from scaling equations of state? And said, no, nobody knows of a relationship like this. So it is satisfied numerically. It does not appear in any other construction that I'm aware of. So this is a nice feature, a nice prediction. So what about the background equation of state? Well, if you have any reasonable background equation of state, you can apply this construction. We've toyed around with the background equation of state, which is just a free gas of particles, non-relativistic gas of particles of mass m. We've played around with massless gas of quarks and gluons. No hadrons at all, just massless quarks and gluons. And this construction works and it gives you physical results. But we want to put in what we think is a fairly reasonable background equation of state. And that is something that Michael Albright and Clint Young and I constructed about 8 years ago. So this is a equation of state, which is basically hadronic gas with either point particles or finite sized particles with excluded volume included at low energy densities, and perturbative QCD at high energy densities. And then there is a switching function that carries you from one to the other. And the switching function is constructed in such a way that it does not induce any critical behavior. It's infinitely differentiable. And so here we show our construction compared to the pressure divided by temperature to the fourth from lattice calculations, and also the trace anomaly or interaction measure. There are 4 parameters in this construction. 2 of them are in the QCD coupling. One is basically the lambda parameter. The other one is a parameter you have to put in to avoid the Landau pole. You don't want the coupling to blow up at any finite temperature or chemical potential. And then there's one parameter for the excluded volume for the hadrons, and then there's one parameter in the switching function. So I would say that this does a pretty decent job. We also compared in a later paper to the square of the speed of sound and to the baryon number susceptibility. The speed of sound, there are no free parameters now. They were fixed on the previous 2 figures. So these are parameter-free predictions. And the square of the speed of sound especially is just, I mean, it looks like a fit to me, but it's not. The baryon number susceptibility also looks very good. I will come back to that at the end of the talk. You see that there might be a slight difference between the lattice and our calculations at temperatures above 200 MeV. But I'll come back to that. That's a minor but interesting point. So how do we determine where the coexistence curve lies? I didn't tell you. I just said there is a function mu sub x of t. That's the coexistence curve. Well, when you look at systems that we think are, well, we know they're in the same universality class. These are in the liquid gas phase transition, and they're atomic systems. What do they look like? Well, there's carbon dioxide on the left, and there's argon on the right. And these are curves of temperature versus density. And these curves are not perfectly symmetric. They're almost symmetric around the critical point, but they have an inverted U shape. And so we decided that's something that we would like to have. We tried a large number of functions, just putting in a parameterization of mu x of t. Typically, we would get out something that didn't look quite physical. These curves in t versus density plane would all curve off to the right. So Tom figured out, was very clever. He said, well, if we want such a symmetric inverted U-shaped curve, what we can do is we can determine the crossover chemical potential by saying that the function R evaluated at that chemical potential for that temperature times the background density is equal to the critical density. And this then tells you what the coexistence chemical potential is in terms of the other parameters and in terms of your background equation of state. It's not something you have to put in. It's something that comes out. But of course, you have to tell what is the critical density, what is the critical temperature, what is the critical chemical potential. Well, these 3 interesting physical parameters are related by evaluating this at the critical point. So R times the background density equals the critical density at the critical point. You can pick any 2 of those 3. So typically people choose the critical temperature and critical chemical potential, and then the critical density comes out. If you look at the critical exponents in the 3D Ising model, they're known very accurately, typically 4 significant figures, sometimes 5. And if you put those in and ask, okay, what are the exponents k and p? Well, k turns out to be 1.209 and p is 1.564. But if you want to choose mean field values, you can do that. Our construction doesn't prevent you from using mean field or anything else. Choose a different universality class. But in the mean field, k turns out to be 4/3 and p is 3/2. So rational numbers, as you might expect. The ratios of the critical exponents give this ratio d plus over d minus. I didn't focus on that, but that was on one of the earlier slides. D is the coefficient of t minus tc in that function delta. So with the actual known critical exponents, that ratio is about 1/3. The mean field value is exactly 1. So then we need some other parameterizations. For example, that function AFT that I mentioned, the delta squared, we know how it behaves near the critical point, but you have to describe how it behaves away from the critical point. And so there are a few extra parameters that are involved. You can see them here. There's an A0, there's a TA, there's a TD. These parameters tell you how rapidly the critical coexistence curve merges into the background. That is something that's not universal. In other words, if you want to see critical behavior right at the critical point, can you observe it when you're 10% away from the critical temperature, or do you have to be 1%, or do you have to be 0.1% close to the TC in order to see the true critical exponents? And that is not universal. So in these kind of constructions, you just can't avoid that. So what does that function R look like? Here's a nice colorful contour plot. It shows R ranges from 0 to 1, of course. It goes to 1 at high temperatures. It goes to 1 at high chemical potential. And the critical point is located at that red dot. And you can see a crease from that red dot curving down. That is the coexistence curve. And for these calculations, we just took a critical temperature of 100 MeV, critical baryon chemical potential of 750. And then with our equation of state, the critical density is predicted, and that turns out to be about 0.4 per cubic Fermi. Isotherms, pressure versus baryon density. Well, these are isotherms 40, 60, 80, 100, 120 MeV. The first thing you notice is that if you start at the critical point, which is a temperature of 100 MeV, and then you just draw a nice smooth curve connecting the ends where those dotted lines are, it's clearly an inverted U-shaped curve. That's one thing. The dotted lines, of course, are the Maxwell construction. Takes you from one phase to the other. If you look at the critical isotherm, it almost looks like there's a discontinuity in the baryon density, but it's not. It's not exactly flat. And the reason it looks that way versus what you typically see in textbooks on the on liquid gas phase transitions is because the critical exponent in this case is almost delta is almost 5, the true critical exponent. So it's very flat versus mean field at critical exponent delta is 3, and then you see what you the smoother shape that you normally see in textbooks, the van der Waals equation of state. Here is the coexistence curve in the temperature versus chemical potential plane. The dot is the location of the critical point. It's a line of first order phase transition. It's solid. Now that curve, it continues onward forever. As you decrease the chemical potential, that curve goes upward in temperature. That curve is always defined. And that was noticed and understood back in the 1960s, where it was pointed out that if you want proper analytic behavior near the critical point, that curve cannot just stop. It has to continue. And that curve has to be defined for all temperatures. Otherwise, again, you would have some extra critical behavior, maybe at mu equals 0. In the curve of temperature versus baryon density, that's on the right. There's the inverted U-shaped curve. It's not exactly a U, but it's symmetric. It's rather narrow. Well, that's what it turns out to be. Not a very large discontinuity in baryon density or energy density. So I know there are questions coming at the end, but this talk should be less than 60 minutes. So if anybody has questions so far, I'd be happy to answer them.
There are no questions in the chat, but if anybody'd like to speak up.
Yeah,
Joe, I have a question for you. So you mentioned that the strength of the critical part of the equation of state is unknown. Which determines how close you have to be to TC for it to be, noticeable. If you had a microscopic kind of field theory, that had gradient squared terms in it and stuff like that, and if you knew what the latent heat of the phase transition was, and let's say the surface energy associated with the phase transition, would knowledge of those numbers be able to constrain how strong the critical part should be?
I don't think so. You need the gradient squared terms, of course, in order to get a
and the gradient
surface
squared terms
energy.
give you the surface energy, right? So
Right. Exactly.
But I was just wondering if there's some way to estimate, of course, for the QCD phase transition, not only do we not know it exists, we certainly don't know what the surface energy would be. So it's hard to, or the latent heat. So it's hard to know. But I'm kind of wondering, if we did know those, would that give us a clue as to how strong the critical behavior would be?
Well, if you knew what it was, for example, experimentally, or if Lattice told you what it was, then I think that might help. But at this point, with this construction,
here it's certainly not, but because you're thinking universally. But okay, thanks.
Joe, excuse me. I have a question, please.
Sure.
I'm just wondering, I understand that the coexistence curve has to persist down to mu equals 0, certainly, but it doesn't look like it matches on to what the lattice finds, does it? Or is this just a different coexistence curve? Because
Yes.
I would have thought it would have matched. No, but it must be, for example, if I went to the chiral limit, this would have to become not crossover, but a line of second order transitions. And that keeps going up. Where does it intersect at mu equals 0? Above 300 MeV, or?
It does not intersect, and it cannot intersect.
Oh, it cannot.
It cannot intersect. So I am perplexed, and other people are perplexed. How does this relate to a chiral transition that would happen at mu equals 0 if the up and down quark masses were 0? I don't know how they're connected. They might even be in different universality classes. Maybe you can shed some light on that.
Well, if you're in the chiral limit, the crossover becomes a line of second order in
Right.
04, and the critical endpoint is a tricritical point. But okay,
Yes.
so I'm sorry, I misheard. Okay, but I'm mystified then as.
So
Okay.
remember, this curve is defined by saying that the R times the background density is equal to the critical density.
Critical density. Yeah. Oh, I see.
Right.
So that's why it can't. Okay, that's why it has to.
Right. Right. So at first we thought, yes, we want the curve to bend over and hit the axis at 150, 160 MeV, and we tried different parameterizations, and you get some non-physical behavior because that's not. Yeah, you introduce extra critical behavior, which should not be associated with a liquid gas transition.
There's a
Okay,
question from Jamie Cartine. Jamie,
Yeah,
go ahead.
hi. Yes, thanks so much. Could you go back one slide to the isotherms? Yes. So are you doing the Maxwell construction here below the critical point?
Yes.
So what do you get if you don't do the Maxwell construction? Can you get the metastable branches?
No, not with this construction. So what you would have to do is what other people have done, and that is you imagine sort of a cubic equation connecting the two endpoints, and then maybe you make sure it's smooth enough, so you match the function and its first derivative in the hadronic phase and then the quark-gluon phase. And so then I have some figures where Tom has made some construction, but you can imagine this going up and then coming down and then like so. Yeah. So that's
Okay.
what you would have to do.
But it doesn't come out naturally from your
No.
choice of the construction. Okay.
No, we thought it might, but because we started with the Q function, which is like the S-shaped curve, but it doesn't come out from that.
But it must be related then to the next slide if you go to the shape of this U coexistence curve, right? I feel like I would expect it to come out as related to this. Interesting.
Yeah, so that the area within this curve is, well, of course, that's where you have phase coexistence. And so our construction gives us the solid curve, but it doesn't tell us what's going on inside.
Okay, thank you.
There's also a question from Feng Li. It's rather long. Feng, would you like to unmute yourself and ask it, please?
It's just I just tapped my question. So so far you have shown an equation of state which coincides with the lattice calculation at 0 chemical potential and possess a CEP at finite chemical potential. So I just wonder, can this formalism can be extended to construct a Green's function which have some coincides with lattice calculation at 0 chemical potential and also present some critical behavior at CEP?
Green function?
Yeah, maybe for example, Green's function of order parameter like baryon number density.
Oh, I will discuss that a little bit later. In this case, let me say explicitly the order parameter is the baryon density.
Yeah.
Now and I'll mention this in the conclusions, but I can say it now too. The background equation of state for the hadronic part has excluded volume interactions only. So it cannot describe nuclear matter. So we are working on a background equation of state, which instead of excluded volume interactions has scalar attractive interactions among the baryons, repulsive vector interactions, something that should be able to describe normal nuclear matter and perhaps all the way up to neutron star densities at 0 temperature. So we have this curve here, and remember this curve is determined mostly by the background equation of state. So once you get down to temperatures of 20 MeV, it's not going to be accurate or valid. But mathematically, you can do it.
Okay, but how about Green's function of the order parameter?
Well,
yeah, you can talk about something like pressure, heat capacity.
Let's leave some of the questions to the question and answer session afterwards. I think we should allow Joe to move on with his talk first.
Okay, yeah, sure.
Krishna had one question. Do you want to ask quickly, Krishna?
Sure. Let me turn my camera on. Hi, Joe.
Hi.
You and then Feng just said that it coincides with lattice at mu equals 0, but the figure on the left side of the current slide, the one that's on the left panel of what's on the screen right now, with that crossover curve sweeping up to very high temperatures, that's not, the lattice finds the crossover at about 150. So,
Exactly.
so the panel on the left looks to me like this is in stark contradiction to what's found on the lattice at mu equals 0.
Well, I wouldn't really say that this is the crossover curve.
So what is the dashed line?
So the whole curve is determined by saying that this function R times the background baryon density is equal to the critical density, and that gives the inverted U-shaped curve on the right. So that curve cannot terminate at the critical point. It has to be continuous, and it has to be defined for all temperatures. So I would not really associate it with this with a crossover.
Okay, and then the other thing I'll point out is that we know that the order parameter is the baryon density only when the first order line is horizontal on the phase transition. Sorry, it's vertical on the phase transition. When it's diagonal, as in your model, it's a linear combination of the baryon density and other quantities. It would be a failure if the order parameter was just the baryon density, given that the first order line is at a diagonal slope in the p mu plane.
Well, I disagree with that, and that's not the way it is in atomic systems like argon and carbon dioxide. But I have a comment on that towards the end. So I will exactly address that just before the conclusion. So
Yeah,
Be patient, be
perhaps you
patient.
could return. Yeah. Go ahead.
okay, so now there is another approach that one can take, and Krishna was one of the people taking this approach in the last couple of years, but it goes all the way back to Schofield in 1969, and this is a scaling equation of state. So the mathematical construction is very different. The goal is the same, but the construction is very different. So the construction goes like this. There are two parameters. Capital R, which is not the same as the one I was discussing earlier. Capital R is a parameter, and theta is a parameter. And the equation of state is described in terms of those two parameters. So that's why it's called a parametric scaling equation of state. So there's the temperature, reduced temperature, is given by R times 1 minus theta squared. There's the magnetization. So this construction was thought of in terms of the 3D Ising model. But if you want to convert it into liquid gas transition, I think it's pretty obvious how one does it. There's the magnetization and there's the magnetic field, and these are conjugate variables. So what you do if you want to describe a liquid gas phase transition, you replace the magnetization with reduced baryon density, and you replace the magnetic field with reduced chemical potential. Those are conjugate variables. And so this has been in the condensed matter literature. And so those two are given in terms of R and theta's parameters that you vary, but there are also constants that enter. There's the constant M0, there's the constant H0, and there is a function H of theta. And H of theta needs to have certain properties. It's almost invariably written as, it's an odd function written in the way I've described here. It's a polynomial in theta, theta plus theta cubed plus theta to the fifth. And those coefficient H3 and H5 have physical interpretations. They're basically telling you about the ratio of critical exponents. The parameter R has a range equal to or greater than 0. The parameter theta has a range between minus theta 0 and plus theta 0. Theta 0 is the first 0 of that function, lowercase h. And by definition, theta 0 is taken to be the positive one. So if you know the temperature, you know the chemical potential, you know the baryon density, you should know something about the pressure. So the pressure has to satisfy the condition dP d mu at constant T equals the density. So that tells you that the pressure has the following form. It's the critical value of the pressure plus mu minus mu c times the baryon density as parameterized above, and then minus product of all these constants times r to the power 2 minus alpha times the function g. And the function g is determined by the function h. So this is thermodynamically consistent then. The critical curve is its position is determined by theta equals plus or minus theta 0, and the critical point is located at capital R equals 0. So if you look above the expression for the temperature, R equals 0 means you're at the critical temperature, no matter what else is happening. It's the critical temperature. Like I've mentioned, H3 and H0 are basically determined by the ratio of critical exponents. Unlike the previous construction, those two ratios are independent of each other. They have to be specified by these two parameters. And then H0 and M0 are positive parameters also that will turn out to have physical significance. So if you look at the scaling equation of state only, I know the font is a little bit small, but on the left, it's the reduced pressure in dimensionless units versus baryon density divided by critical density. And you can see the Maxwell construction there. It all looks fairly reasonable. As Krishna was mentioning earlier, if you plot the temperature versus the baryon chemical potential, there's the critical point and the line is vertical. And of course, that's not what you expect from QCD. But this is the scaling equation of state only. There's no background. So here's where we differ from Krishna and other authors, Nonaka and Asakawa. We modify the scaling variables. So the temperature is the same. The reduced baryon density is the same. But instead of writing the reduced chemical potential as mu minus mu c over mu c, we write it as mu minus the coexistence chemical potential as a function of temperature. So as I will point out later, this maintains the baryon density as the order parameter. Now the pressure, instead of multiplying the background pressure by a function, what we do is we say that the total pressure is constructed as the background pressure plus the critical pressure P star, which is the one that I showed, which is the one that I showed on the previous page, except for the replacement of a redefinition of a couple of the parameters. But it's the same function multiplied by a window function. And this window function suppresses the critical contribution to the equation of state when you're away from the coexistence curve. And again, in constructions like this, somehow you have to smoothly match onto the background. And there's no agreed upon universal way of doing this. So we say there is a window function. We'll give a parameterization for it in a bit. The background is the same as the one we used before, except now we're going to use point hadrons just for fun, just to show that you don't have to use the same background equation of state all the time. And now if we want to have, of course, this is our desire. QCD may not be this way, but we want an inverted U-shaped coexistence curve in the T versus density plane. In this case, the background density evaluated at the coexistence chemical potential is equal to the critical density minus the N0 that appears in this formula for P star. So on the previous slide, you notice for the pressure, there is an NC that appears explicitly here. Whereas when we do this construction, including the background, we replace that NC with an N0. And so that's how the N0 enters. So now, okay, this is now what determines the coexistence curve. I'll emphasize again, you could parameterize the coexistence curve in other ways. This is just the way we choose to do it because it does give that symmetrical inverted U-shaped curve. But if you want, if you're satisfied with some other shape, then you can choose, you can parameterize mu x of t any reasonable way that you like. So this is function theta as a function of t and mu. I think similar figures have been seen in other papers, a couple other papers on this topic. But there you see, we choose the critical temperature in this case to be 120 MeV. Why not? I thought maybe it should be higher than 100. Critical chemical potential is kept at 750. In this case, now with this point hadron equation of state, the critical density is higher. It's 1.3 inverse cubic Fermi. So you see there's a discontinuity along the mu axis, and you follow that discontinuity down, it eventually emerges into the critical point. So now if you make isotherms pressure versus baryon density, well, there they are. That's what the curves look like. The critical isotherm is at 120. That's the green curve. Again, it looks flat, but there is no discontinuity in the baryon density there. Again, because the critical exponent is almost equal to 5. The Maxwell construction, you can see it, those are the dotted curves. You imagine starting at the critical point and connecting the ends of those dotted curves. That's the inverted U-shaped curve. Also then on the right, we show the baryon number susceptibility as a function of temperature. And so there it goes, it diverges. It's not symmetrical around the critical temperature. Typically, it's not in real systems. That's what it looks like. The coexistence curve and the T versus mu plane, there it is. It's not exactly the same function as you saw earlier, because we're now using, well, first of all, it's a slightly different construction. It's the parametric scaling equation of state, number one, and number two, using point hadrons instead of excluded volume approximation. But there the curve again, dash curve continues on up. And again, it has to be defined and exist for any values of the temperature. It can't intersect the temperature axis. Inverted U-shaped curve in the T versus density plane. That's what we get. And you can play around with parameters and do lots of things with these, but these are just parameters we chose for illustration. What about that window function? So there's the coexistence curve. We've drawn it again, and there is a window function which is supposed to cut out the critical behavior as you get away from the coexistence curve. So again, there's no unique way to do this. You just want to make sure that whatever window function you put in does not generate any extra critical behavior, and it doesn't generate any unphysical results. So the first exponential is 1 along that whole curve, including the dashed curve. And when you get away from the dashed curve or the solid curve, it goes to 0 exponentially. And there's a parameter, a power j, that you can choose. The power j, we chose it to be 1 to begin with, but then there's the question, well, what happens if you go to an pure imaginary chemical potential? Then that exponential becomes increasing instead of decreasing. Well, then you choose the parameter j equal to 2, and that solves the problem. And the curves you get are almost indistinguishable, whether you choose j equal 1 or 2. And I've even forgotten whether this is the original j equal 1 or the modified j equal 2. But that only suppresses behavior away from the full curve. You also want to suppress the behavior when you're above the critical temperature. So that's the second factor. And we just put in, again, an exponential. So there's another parameter, lowercase t0, that enters there. If I was drawing these curves by hand, the window function by hand, I would try to make it a little bit smoother. That's something that we can improve upon in the future, but this is what we did. So some comments. The lattice data we originally compared to Michael and Clint. That was lattice data from 2008, 2010, 2012, thereabouts. And there have been more accurate calculations since then. So, okay, let's look at our background equation of state with the excluded volume interactions, just to see, well, how much do the parameters change and can we still fit the data? So we tweaked those 4 parameters just a little bit, and we reproduce the lattice results, I think, pretty well. So the pressure over temperature to the 4th is on the left versus the temperature. The interaction measure, trace anomalies on the right versus temperature. And excluded volume 1, excluded volume model 2. I won't get into those. Those are slight differences in how you do excluded volume for hadrons. But I would say that they represent the data pretty well. So the parameters are fixed, again, by these 2 curves. These 2 curves fix those 4 parameters. There is a parameterization of the lattice, which is in the paper by Barotto. Krishna is a co-author on that paper. That's a good parameterization too. Now that the parameters are fixed, we can look at the baryon number susceptibility, chi2. We can also look at chi4. They've been computed by the lattice. So if you look at chi2, first of all, you notice something that I had mentioned much earlier in the talk. The lattice calculations are there. It's these, the lower one, and the excluded volume, well, crossover equation of state is the red curve above. And you see, well, there's a difference of, I don't know, 5, 6, 7% once you get above temperatures of 200 MeV. So this is not related, this small difference is not related to critical behavior, and it's not related to the hadronic equation of state. It's basically telling us that whatever perturbative QCD results we're using are giving a susceptibility which is a little bit too high. And Tom has played around with the numbers a lot, and it's difficult to bring that red curve down. There is a way to do it, but I don't quite understand or believe the physics behind that. So that's an open question. Chi4, of course, the error bars are quite big, but again, this is a parameter-free prediction from our model from the previous two figures. Finally, to Krishna's point. So a long time ago, 2005, Nonaka and Asakawa invoked, I think for the first time, this parametric scaling equation of state applied to the QCD phase diagram. And so in order to avoid that vertical curve in the T versus mu plane, they did a rotation of the axes. So they expressed the reduced temperature and reduced chemical potential in the following way. So remember, R times 1 minus theta squared, that was originally the reduced temperature. So now they make a rotation between that and the R to the power beta delta times H. So W is a parameter, rho is a parameter, alpha 1, alpha 2, those are angles. And so we were interested in knowing what is the order parameter. When you do this rotation, you're kind of mixing up temperature, which is associated with entropy, and chemical potential, which is associated with baryon number. So after a little bit of Googling, we find a nice paper by Ruhr and Merman, Bizrev A, 1973, in which they say, okay, if you do something like this, they didn't do this rotation, but if they considered general critical behavior. So if you do something like this, then you can figure out that the order parameter is a linear combination of the derivative of mu with respect to zeta and the derivative of t with respect to zeta. Now, at fixed tau. A tau is that combination R times 1 minus theta squared, which would basically the reduced temperature in the original scaling. And zeta is the other one, basically the reduced chemical potential. And so when you calculate the order parameter for this parameterization, it turns out to be a linear combination of the baryon density, N minus NC, and the entropy density, S minus SC. And then we were wondering, well, what about the critical exponents? Do they turn out to be correct? They do. So in this case, even though the order parameter is a linear combination of baryon density and entropy density, the critical exponents are still all fine for the heat capacity, for the baryon number susceptibility, et cetera. The construction that we give, our reduced temperature is the same as before, but remember, instead of a mu sub c here, we put in the coexistence chemical potential, mu sub x of t. And when you calculate the order parameter near Tc, and in our case, it turns out to be just the baryon density. So I think that's interesting. I don't know if it has any physical significance. The fact that the baryon density and entropy density, as far as I know, have the same critical exponent. I don't know if it has any physical relevance or not. So finally, let me come to the conclusion. Okay, so I've talked about all this, why it's important, and everybody knows why it's important, and which universality class we think the critical point might be in. The constructions I've described today have the freedom to describe other universality classes. You have to put in the values for the critical exponents. So they could be the true ones for 3D Ising and liquid gas. They could be the mean field values for those systems, or maybe it's QCD has a different universality class. That's, you have the freedom there. So you also like to know how many parameters these constructions have. Well, the critical exponents and the ratio of critical amplitudes are universal. So I would not count those as parameters. Once you specify universality class, you know what those are. The construction number one, the first one that I described, has 4 extra parameters. And these extra parameters are, again, associated with how do you merge critical behavior into the background. Construction number 2, which is the one with the Schofield parametric scaling equation of state, has 6 extra parameters. Now, the difference between 4 and 6, one of those is the fact that the construction number 1 predicts the ratio of how the ratio of critical exponents are related. So that takes away 1. And the other one, well, that's just in the parameterizations. We need to take equations of state like this, put them into hydrodynamic modeling and compare to data. Now, there's a long-standing question is, if you have a first order phase transition in a heavy ion collision, do you do a Maxwell construction? That's what we did decades ago when Bjorkane first came up with his hydrodynamic model. But of course, in reality, timescales are short enough that you're probably not going to be in equilibrium to have a Maxwell construction. So how do you pass through from one phase to the other dynamically? And that was pointing to Scott's question about adding gradient terms to the free energy. Finally, we are, like I mentioned, we are working on more realistic background equations of state, particularly the hadronic part, in order to describe neutron stars and neutron star mergers. But also the perturbative QCD equation of state at small temperatures and chemical, well, temperatures in the order of 200 to 500 MeV in small chemical potentials, that seems to be in slight disagreement with Lattice. So that's still an open problem for people to look at. So thank you very much for attending this morning and for questions.
Rob, are you still there? I think Rob has left. He had to go to a different meeting. So I'm taking over as chair.
Okay.
And I think I don't see any more questions in the chat after we interrupted you after your first half, but I see a number of hands, and I think the first one up was Joachim Stroth. If you could open your mic and ask your question.
Yeah, thank you for this nice presentation. So I have a question. So I understood that basically you said the order parameter would be baryon density. Did I understand this right? So you're basically talking coexistence line as a quark gluon to hadronic gas transition, right? Nothing
Yes. So
related to chiral symmetry restoration.
So my understanding is that the order parameter should be the baryon density. However, there apparently is nothing wrong with taking a linear combination of the baryon and entropy densities. It doesn't, the critical exponents are still turn out to be fine. So
sorry, the other question, this connection, then you can also make a statement about the latent heat at this rate if you would cross the boundary there. And
yes, there is a latent heat, and I apologize. I didn't show any figures for that. We didn't put those figures in our papers.
That would
There
eventually
is a
be-
latent heat, and the latent heat obviously goes to zero at the critical point.
Yeah.
But I
it
should
would
have
be-
had it. I should have had some figures to show you how large it is.
The reason why I'm asking is that, of course, there we are discussing whether that could be visible in the dilepton emission. So if there's a latent heat, I mean, it eventually would mean there's a time system has to spend while radiating, and it would be good to try to quantify how much one could expect there in terms of like delay of the expansion, whatever. And that should
Yes.
be connected somehow to the latent heat. I think would be very interesting.
Yes, I agree. That's work
Thank you.
still to be done, at least from the point of view of these constructions of the equation of state.
Okay, thanks.
I think Jamie was the next hand up.
Yeah, okay, thanks. Can we go to the pressure density plane?
This one?
Yes, perfect. So above TC, so this yellowish green line, is that really linear or is there an inflection point?
There's still a slight remnant of critical behavior.
Because if we think
Yeah.
about just the Landau-Ginzburg free energy as a function of the magnetization, which would basically be the analog of this plot, you should see some inflection point above TC. Not
Yeah,
just a flat curve, but something.
Yeah, there is a hint of it here. It's maybe hard to see numerically, and this is a temperature of 1.2 times TC, I think.
Mm-hmm.
So if you go down to 1.1 TC, I think you would see it a little bit more clearly.
Okay, so there's something there if you are close enough
Yes.
to the critical point.
Yes,
Okay, that was it.
And-
then. Thank you.
and of course how far up in temperature that extends depends upon your window function. How
Mhm.
rapidly do you cut off the behavior? And that's not universal.
Okay, next one is Joachim Krefer.
Hello, thanks for the nice talk. I had a question. Is there any prescription for the value of the density at the critical point? Because I think I saw two different values, and do they produce like an acceptable equation of the state at the zero chemical potential in comparison with the lattice, for example?
So remember, there in both constructions, there is a formula that relates the critical temperature, the critical chemical potential, and the critical baryon density. And you can choose any two of those, and then the third one is determined. So we decided to choose TC and μc. So the μc is the same for both constructions. For TC, we chose it to be 100 for the first construction, 120 for the second. The baryon density for the first construction was 0.4, and for the second construction was 1.3. So part of that difference is due to the fact that the critical temperature is higher, but part of it is also because for a given value of T and mu, if you just look at the hadronic equation of state only, and you look at the same T and mu, the baryon density for point hadrons is higher. And that's because the excluded volume prevents the baryons from being too compactified. So it naturally leads to a smaller baryon density at the same T and mu. So both equations of equation of state, let me go back and make the comparisons. Well, let me do the more recent one. So this is comparison to the more recent lattice data. It's very similar to the older ones, but yes, it reproduces the pressure at mu. These are all at mu equals 0. We should have said. So this is the pressure at mu equals 0 interaction measure. That's how well it reproduces it. The susceptibility chi2 on the left, chi4 on the right. That's the fourth derivative. Now, when you get to the fourth derivative of the pressure with respect to chemical potential, that's really pressing your knowledge to take 4 derivatives. So your function is really being examined under a microscope. And it doesn't do too bad. I mean, I would say it's acceptable for studies like this. The baryon number susceptibility at temperatures above 200 MeV, I think that's an issue with the perturbative calculation. And so that's an open problem that I don't think anybody has noticed that before.
I see. Thank you. Thank you so much.
So if you want to study that problem, you don't need to do hadronic equation of state. You don't need to do a switching function. Just compare the perturbative calculations for the pressure against the lattice.
Oh, I see. Thank you. Thank you.
Yeah, I'm sure Mike Strickland would have to say something about that because he studied that question, but I don't think he is on the call. So let's take the next question from Krishna.
Yeah, so hi, Joe. Thank you very much for the talk. This was great. Yeah, so it's a comment, not so much a question, related to the comparison you made near the end of your talk. So all of the phase transitions that you've been discussing and that we've discussed today are in the Ising model universality class. This includes the liquid gas transition in argon or carbon dioxide, or the liquid gas transition, non-relativistic liquid gas transition as described by van der Waals equation of state, which is similar, or the liquid gas transition in various alloys, or the liquid gas transition in low temperature, low energy nuclear physics, or the QCD transition, as at least as we understand it today, as you've described. But the statement that the order parameter is the baryon density is not a universal statement. In the Ising model itself, it describes magnets. The order parameter is the magnetization. It's not a density of anything.
Right.
In the QCD phase diagram, if you play around with quark masses like the strange quark mass and so on in such a way as to move the critical point not to where you had it, but to move the critical point in a way that's unphysical, but still you can do as a theoretical physicist, to move the critical point quite close to the vertical axis, so move it towards the left, then the crossover line and the first order phase transition line are almost horizontal. And the order parameter for the Ising transition in QCD has very little to do with baryon density. It has a component of baryon density, but that's a minor component. It has much more to do with the chiral order parameter, the entropy density, the energy density. There's discontinuities in the chiral order parameter, in the entropy density, in the energy density. Baryon density is minor. If you fiddle with parameters to put a critical point in QCD with the wrong quark masses, but you put a critical point at a mu of 50 MeV, the baryon density is a completely minor player there. And now, of course, as you move the critical point to more realistic values of mu, 400, 500, 600 MeV, wherever you choose to put it, the baryon density becomes much more important. But it is a non-universal choice to assume that the order parameter is equal to the baryon density. That's a non-universal choice that you can make in modeling, as you've shown, and get reasonable results with no pathologies, as you've shown, but you are forcing the Ising model into a particular non-universal straitjacket by requiring its order parameter to be 100% baryon density, as opposed to allowing it to explore what QCD may itself describe. And that's the comment that I wanted to make.
Okay, very good. I actually, the last bullet point here, we checked that the order parameter is n minus nc only near TC. We just did a Taylor series expansion. If you're well away from TC, I'm not sure that the entropy might not enter.
Even near TC, it won't be just n minus nc unless the phase transition. If the phase transition line is vertical, then the order parameter is conjugate to mu. But when the order parameter is not conjugate to mu, there's no reason for it to be just the baryon density.
Okay, thank you.
Are there any other questions? I see a hand from Scott Pratt.
Yeah, I wanted to just making a comment, and I hope you have a comment on my comment, because I can't say how confident I am in what I'm going to say. But I think this reinforces what Krishna just said. If you think about the equation for non-relativistic atomic type systems, the gradient term that you have in the field theories involve the baryon density, and that's supposed to involve, so you have a term like kappa rho grad squared rho, and that's just or motivated by attractive longer range attractive interactions between atoms or argon atoms or whatever it is that you're doing, and that's because that energy, the thing that's the long range, which is giving you all this critical phenomena, longer range, that interaction is a force that couples to baryon density. I think that if you wanted to do this more generally and talk about a field theory, where both the energy density and the number density were variables that could fluctuate, you could imagine gradient squared terms in some linear combination of those. And I think that's what happens in QCD, is that the gradient squared term isn't coming so much because baryons attract one another. It's because you have a chiral field, which depends on the baryon density and the energy density. And of course, it's very natural in a field theory to have terms that look like the gradient terms involving the chiral field. But if the chiral field depends on both energy density and baryon density, then it's very natural and if the gradient term is coming from gradients of it, then it should end up with some, when you transpose that to how does that depend on energy and on epsilon and rho, you're going to get cross terms in it. Maybe even, of course, at rho equals 0, it could only be gradient squared of epsilon. And that suggests that then when you do the conjugate variables, you're going to get a linear combination of t and epsilon. So I think as long as the gradient terms that are giving the field theory, that are driving the field theory and driving all the critical phenomena, are coming from a sigma field. And if that sigma field depends on both the energy density and the baryon density, then it would be very natural to think that you were going to get some kind of off-axis behavior, like Krishna was describing.
Okay,
If
I agree.
Krishna agrees with what I said just now, but I think and that's the physical difference between an atomic system and the QCD system, is the physical origin of what's giving the gradient terms in the field theory in the first place.
There's
Okay,
one
this is-
comment. Yeah.
The comment, but I would love to comment on my comment to see if people agree that that's really why we expect atomic systems and QCD to be fundamentally different.
I guess I'm not sure I'll agree to the word why, because I'm not sure what's causal in what you said, but I think you're giving a different words, a good description of important differences, non-universal differences between the van der Waals atomic systems and QCD.
Well, let's say there's a chiral field sigma, and I think the field theory should have a gradient term involving just sigma.
Exactly.
But sigma isn't conserved; it's a function of the energy and baryon density.
Absolutely.
But I can write that gradient terms in terms of gradients of energy, density, and rho. Correct. And I will get terms that involve, grad epsilon times grad rho, and grad of epsilon times grad epsilon, and so on. It won't just be grad rho times grad rho.
Exactly.
And then the conjugate variables will then turn into t, some combination of t and mu, not just mu.
Exactly. And so this is why in our approach, there's 6 unknown parameters, which have to do with how you map what you just described into the Ising model critical equation of state, or map the critical equation of state onto the QCD phase diagram, however you look at it. Because we don't claim to know all the things that you just described, that you have to allow you have to allow for a mapping. But what I would say is that it's too simple. Many of us, if I go back 20 years myself, many of us talked about this in a way that was just as straitjacketed, but from the other side. Many of us 20 years ago talked about this as if this is the chiral transition, and the way to describe it is just fluctuations of a chiral order parameter, full stop. That's just as constraining and straitjacketing as saying, well, it's just baryon number is the order parameter. I mean, as the chiral order parameter fluctuates, that corresponds in a hadron gas model to fluctuations in the masses of the baryons, which affect everything. They affect the energy density, they affect the entropy density, they affect the baryon density, they affect everything. So the fluctuations of the chiral order parameter, when you translate it into hydrodynamic variables, fluctuations of the chiral order parameter correspond to fluctuations of the baryon density, the entropy density, the energy density. Which I think is what you're saying. Also.
Yeah, and I say if you did want to start with the field theory would have terms that would look like gradients involving both the energy and the numbered and the charge density. And that's what is fundamentally different.
So I think we're agreeing with the others. We should let Joe comment, since he is, after all, the speaker. And I also see that Paolo Parato has his hand raised.
Yes, I love this discussion. This is why we're having these BES seminars. Joe, do you want to interject, or would you first want to listen to Paolo's comment?
Well, let's hear Paolo.
Paolo.
Hi, thank you for the talk. Yeah, it's basically the same thing that Krishna and Scott are talking about. My understanding of the equation that you showed from Rur and Mermin is that this hence it's the capital psi. This relation is forced once you choose the parameter. It's not just a choice that you can make. You could not change psi without changing according to the parameters, and so that's why the way, if I recall correctly, the way it's written in the paper, you cannot just choose psi as anything you like, except if you force in this case, the parameter alpha 2. In your case, it will be alpha 2 equals 0, if I'm not wrong, or 90 degrees, one of those two. But maybe I remember wrongly the way that the paper is written, but I remember it being something that forced this relationship.
It's really hidden away in that paper. It took quite a while to find that. My comment is, I'm not convinced that there is a critical point. I would not be surprised if there is none.
Yeah, I guess we probably all agree on that.
Well, on that note, maybe we have reached the end of the discussion. Let me thank the speaker, Joe, for a wonderful talk, and the audience for a wonderful discussion. And let's meet again next week.
Thank you.
Any more comments from the organizers? Yi?
No, but thank you so much. See you next time.
Okay. Bye-bye.
Bye. Thank you so much, Joe, for for giving this talk early in the morning.
You're welcome.
It's awesome, Joe. Bye.